Get down. Get down.
Bang, bang,
Down the Marco.
Hey yo. Hey yo. Okay, so I figured out it's my Nightbot. It's Nightbot that's not working. But I don't know why Nightbot's not working. Yeah, what's going on, Nightbot? What's up, Crumb? I have to re-invite it? How the fuck do I do that? Yeah, because now that I think about it, I haven't seen Nightbot in a minute. What's up, Crumb? How to autoplay Nightbot down? Is Nightbot down? It appears Nightbot 6 days ago. An issue, but today is not responding to any commands and chat logs. Alright, yeah, this is my problem. Yag, what's up? Yeah, I got put in double overtime for you because I remembered I have a dinner to go to tomorrow. So I wouldn't have been able to edit that video, so I got it in there. Okay, I gotta re-invite it, you're right. So how the hell do I do that? Wow. Come on, Crumb. That's like you throwing a Syntex sticky bomb on yourself. Okay, so let's Google that. How do... Nightbot dashboard. Okay, so now let's look at my mods. Is Nightbot on that list? Nightbot is not on that list. All right, moment of truth. Nothing. Yeah, it says part channel. I don't know what that means. Leaving channel. All right, now it says join channel. Am I on the right one? Ensure you're modded. Mod Nightbot. All right. All right, yeah, so I did that. Hey, there it is. All right, we're back. Okay, cool. Took forever. Got our links back. All right, we're in charge, people. Look alive. We are in charge. Join the race. Get your name in the race. All right, well done, Crumb. You are a scholar and a gentleman. Metal Crumb, everybody. Metal Crumb, everybody. All right, so what do we want to do tonight? We got a few topics we want to talk about for sure. But hopefully you guys had a great day. What's today? Today's Thursday, man. Brutal. We do have a little bit of work that we want to do. Tani already sent me an email, a message on Discord, and said she will not be here to assist me in the work that she was trying to help me with yesterday. So we're gonna ride it alone. But also, I got a secondary form from Google. So clap it up. Google sent me a secondary form to fill out. So we'll take a close look at that. It sent it at like 7:00 tonight. And asked for it to be submitted by Monday. But we got a busy weekend, so we're going to try and get that knocked out. Me and Yak posted our last debate. You guys should definitely go check it out. We posted our last debate, and it went real smooth. Today we're going to talk about LinkedIn's AI system literally just stealing everyone's information. Not stealing, or maybe stealing. I don't know how best to describe this. It's definitely, como se dice, a little sus, because we'll talk about it. But for sure, there's no green screen behind me because my mother burnt it today while using the iron, because for some reason, she saw that extremely green screen cloth material and thought to herself, oh, this is an extra protected layer that Hero puts on his ironing board. So there's a skit. There's a skit coming for that soon enough, right? There's a skit coming for that soon enough. But just wanted to say, shout out. We're like 100 hours from breaking our view record on YouTube. Hours watched. The last two videos that kind of revolve around tech layoffs and working from home really did really well. So we'll keep the energy going, and we'll put up another one. Put up another one for the people. Closing out the powerful weekend, and then we'll got dinner with the friends and family tomorrow. And I'm going to a show on Saturday, so that'll be nice. And I think my house will be empty for 24 hours. I'm not sure. Unless there's somebody's girl about to get smashed this weekend. It's a dance on TikTok. It's pretty funny. It's a dance on TikTok. It's pretty funny. I don't know who Milli Vanilli is. Ren, are you NetDev? Are you showing your age right now? Hey! Don't call me young with that old ass reference. Don't call me young with that old ass reference. The 90s are that far away. The 90s are, in fact, 20 years ago. The 90s have a mortgage and student loan debt right now. The 90s can legally rent a car in all 50 states. The 90s have care about their credit scores. Oh no. Okay. I don't have any, so all of my events are gone. I can't see any of my mini feed events apparently. I do want to test it though, but I can't test it, so hopefully if someone follows raids, all that good shit. Follows, raids, all that good shit. We'll be able to see it eventually. I can see you guys on Instagram. Don't think I'm ignoring you. TikTok, I am ignoring you. Because y'all some hoes. No, I'm just playing. But, yeah. This is going to be a short one tonight because I got to wake up at 8 o'clock because of money, y'all. Because of money. It's tragic what a brother will do for $1. Yeah, holla. All right. But I do want to play some Call of Duty this weekend, and we got a huge chapter to finish in the comic book, so super excited. Super excited. It's Thursday. Tomorrow's Friday. We made it. Y'all should be proud. Stand proud. We made it. All right, let's get this set up. Oh shit. I keep hitting the wrong button. Man, that's kind of crazy. Anybody watching the game? What's the score right now? I just remember it was 7-0, and I had to get ready for the show. All right, cool. We're all caught up. Finally. Sheesh, that took like 20 minutes to do. Okay, let's get into it. I'm sorry. Let's. All right. Hey Crumb, you want to remind me to turn back on the alerts when the news is over? I know it's probably beneath you, but I appreciate you. Hey. Okay. I don't know anybody if I don't know if y'all need to know this or hear this, or somebody nobody's ever told you. Stop applying on LinkedIn and Indeed. It's a trap. It's a trap. It's a trap. How you doing? My name is Hero. This is Coding with Strangers, and I want to talk about something. Look. Could you imagine you apply to like 600 jobs and you have like 4 different variations of your resume, 18 variations of your cover letter. You even made a slide deck, a 12-page PowerPoint to kind of bring home the point about what you do, how you do it, how you did it. And you go through all that work. You get about an average of 15% callback. You get of that 15%, you get and these are all cold cases, right? This ain't no referral shit. This is some cold case shit. And on that 15%, you get 10 offers that you outright decline just because when you get to a certain dollar point, it's about your sanity. It's about your peace. The dollar amount doesn't matter anymore. When you live in the middle class and you make over a certain amount, the money doesn't matter. Your peace matters more than anything. And then you do all of that just to find out that the job you really want, you can't get because you're not qualified for it. But here's the kicker. You lie on your resume, you go through the interview process, and you actually get that job. Could you imagine? And then in your shock and in your bravado, you panic because now you got to learn how to program. You got to learn how to sift through query databases, and you got to create landing sites and S3 buckets and all of these different things you never knew. You got to learn it. So you turn to the internet, you make a few videos on YouTube, you stream every Monday through Thursday, and you call your channel some bullshit like Coding with Friends. and then instead of, probably taking full advantage of this opportunity, you go back out into the to the workforce. You go back out to try your luck and your new skill set to see if you can land a job. But what if I told you LinkedIn is using your frequency of posting, your frequency of applying to jobs, and anything you do on their platform to basically isolate you and make sure you don't get a job? And you're probably thinking to yourself, that's crazy. LinkedIn's whole purpose is to get a job. I told you. Stop. It's not. Every time you hit that easy apply, your shit just goes into a void. They have to fill a quota of sending random applications to these companies to fill their quota, and you're considered a number in that. But we got a story today that kind of talks about LinkedIn has started harvesting people's posts for training of AI without asking you to opt in. And I'm going to say this right now. With the whole Apple AI thing coming out, going to a few AI related events, there is a place in the world for optimized large language models, but AI in 1 to 2 years here is going to flatten out. They were bragging about this the other day. They were bragging about this. Hey, I'm a busy product manager and I don't have enough time to be on all these calls. And now with this new Teams AI feature, it can go to meetings for me and send it to me in a text. You know what that's called? That's called an email, sir. Did you just put a bow tie on shit and sell it back to me? That's called an email. So I think we've hit the pinnacle of what AI is going to do. And now that companies are starting to figure out there are two types of companies that can benefit from AI. Companies that have a large amount of language, companies that have large amounts of information about people that they can sell as data, which is normally the broker of information, large information that can be sold, and companies that want to take that information to then in turn sell you ads. The vicious cycle continues. But as much as we've talked about how finding jobs in today's market has become so difficult, and it's become more difficult because for some reason CEOs' pensions keep getting higher and higher, and they just can't figure out why they have to keep letting go of more and more people. I'll say this to the death of me. Satoru Iwata literally took no salary when the Wii U didn't hit the quota it was expected to do. And I challenge you to show me one of the FANG CEOs who are willing to buckle that situation. You know, how many yachts do you need? There's only 7 days in a week. How many yachts do you need? But I digress. Let's get into this and figure out what bull LinkedIn is up to. LinkedIn started harvesting people's posts for training AI without asking for opt-in. You'll have to opt out if you don't like it. EU and a few others expected. LinkedIn started harvesting users' generated content to train its AI without asking for permission. I don't know what is this word?
Angering netizens.
Angering netizens. Who wrote this? Simon Sherwood. Okay, this is from the Register. I get it. You're probably not as big as the other publications, but come on. You're writing this for the people. Microsoft's self-help network on Wednesday published a trust and safety update in which senior VP and General Counsel Blake Wallet and revealed LinkedIn use of people's posts and other data for both training and using in generative AI features. It is doing so, he said. The site's privacy policy had been updated. We note this policy link to FAQ that was updated sometime last week, also confirming the automatic collecting of posts for training, meaning it appears LinkedIn started gathering up content for its AI models and opting its users in. well before Lawit post and updated privacy policies advised. So this is already underhanded as hell, right? They did this a week ago. They put out the FAQ update a few days ago, and now they're like, oh, you guys don't like this? Well, you guys can opt out. There's a way to do it. We posted it 2 weeks ago, but it's just crazy how that they've already. It's LinkedIn. They've already gathered everyone's information, so now you have to get them to remove it from their database. And this is problematic for a lot of reasons. I don't know if they'll mention it here, but we'll talk about it if they don't. But this is super problematic for one of the two biggest places to go and look for a job, to be able to gather information on you. And remember, that information, if LinkedIn is on your phone, that means they can also track your geolocation. Imagine your job buying the information of its employees to see where their employees are living, where their applications are coming from, if one of their employees are sending out applications. A very problematic situation we have here, but we'll get into it. The FAQ says that the site's built-in generative AI feature may use your personal information to do things like automatically suggest stuff to write if and when you ask it to, and that your data will be used to train the model behind those features, which you'll have to opt out of if you don't like it. Okay, so let's also discuss this real quick. Can we all admit that those prompts that they give us is dog water? It's some of the worst prompts, the worst suggestions are given to me by AI. And the fact that they all sound the same, you can immediately tell when someone has sent you a response using AI. And it's a little bit disrespectful. It's a little bit disrespectful. Because why don't you have the time to write me something polite? Right? It's one of the worst feelings now, and you're starting to see it more in emails. I've already told my nurses, like, look, don't put this bullshit in none of your, like, if you're writing a patient's chart and you're using AI, we're going to have a problem. We're going to have a problem. Because if it starts hallucinating on what it thought you were supposed to be writing and you miss that, I'll have you guys writing this shit with pen and paper and scribing it out, dictating your notes out later. So we put a very big kibosh on this. And shout out to my hospital for just blocking ChatGPT altogether. You can't use it on the internet, on our internet. We're also told that using LinkedIn means the outfit will collect and use or process the data about your use of the platform, including personal data, your post, articles, how frequently you use LinkedIn, your language preference, and any feedback you may have provided to our team. Damn, so that's crazy. So they were able to see if you're on LinkedIn while you're supposed to be working. It's just an invasion of privacy at this point. Very problematic. We're also told that using LinkedIn means there's some good news for users in the EU, Iceland, Norway, Liechtenstein, both of them. Okay, there's two of them, and Switzerland, as their data is being used to train LinkedIn AI, all and won't for the foreseeable future. So all those countries mentioned in the EU aren't going to have their information used. It's amazing how the EU is literally leading the forefront in protecting people's personal data, and America just can't seem to get on track. The document also states that LinkedIn seeks to minimize personal data in the data set used to train models, including by using privacy-enhancing technology to redact or remove personal data from the training data set. We can't get the data. We can't get the large language models to spell strawberry correctly. I don't think this is going to work. But the FAQ also contains the following warning: the system may provide someone else info if asked in a certain way. So a prompt wizard could basically get the AI system to disobey the original programmed language and use this to literally siphon information. So they're openly admitting. Did I just hear this correctly? Did they openly admit that your information isn't safe on LinkedIn? That anybody using that generative AI system can probably spoof your information. The warning is members or customers may provide personal data as an input to generative AI powered features, which could result in personal data being provided as an output. For example, if the member used the generative AI writing suggestion feature to help write an article about the best advice they've got from their mentors, they may include the names of those mentors in the input, resulting in the output generative AI writing suggestion. The Microsoft social media outfit also last week admitted an article titled "Control Whether LinkedIn Uses Your Data to Train Generative AI Models That Are Used for Content Creation on LinkedIn." The text explained how it's possible to opt out of the AI scraping and points to setting called Data and Generative AI Improvement that offers a single button marked "Use My Data for Training." So just in case you guys want to use that, I'll put that in here for everybody. And it'll also be in the description below with this article. Those off use my data for training, collecting data. The button is on position until it moves to off. Users' anger cannot therefore be surprising on LinkedIn. Big Tech has mostly used scrape first, settle the lawsuit for the penance later approach to finding the content it needs to develop AI models. Forget about the concept of begging for forgiveness rather than asking for permission. Neither question is asked at all. LinkedIn could not have been unaware that likely backlash, making the approach very curious. That's super funny. That's super annoying. Users' anger cannot therefore be surprising on LinkedIn. It is not hard to find the service move described as breach of trust, along with a rush of posts advising users how to turn the scraping off, which thankfully is not hard to do. Click on the LinkedIn profile setting, then go to data privacy, look for an item labeled Data and Generative AI Improvement. Click the single button there to opt out, then go back to wading through the rest of LinkedIn. So this is super problematic for a lot of reasons, and we've talked about LinkedIn in the past. And Ed Reed is the CEO of LinkedIn, who also sits on the board of Microsoft, one of the biggest employers in the world and one of the biggest companies in the world. And it's one of those oxymorons where the biggest company in the world needs the government to believe that they are employing people, they are constantly growing, and the person who is in charge of collecting data on who's applying to jobs, and then in turn giving that data to the labor unions and the labor markets to say, yes, people are hiring. The self-check balance situation here does not look good. But once again, I've said this before and I'll continue to say this. AI is starting to run its course, and AI is going to be used to get information from people. And why is this problematic? Like, maybe I'm being a doomer here. Maybe I'm on my front porch screaming at clouds, or maybe I believe that they're so fucking greedy. They're so goddamn greedy that they'd be willing to keep you in a position that you can't get out of. For example, if LinkedIn knows where you're applying, who you're applying to, how frequently you apply to them, how much time you spend on LinkedIn. And we know this for a fact because if you're not one of their pro members, and you should never sign up for their pro members because the first free month is free, but they only give you half of the access to it, and they won't give your application full privileges until after 3 months of paying them. So they're going to just get 3 months from you up front, and then they'll actually start helping you. But LinkedIn literally tells you at the beginning that they're not interested in getting you off the app. What sense does that make? It's like a dating app. like Hinge, Tinder. On Tinder, I'm 6'5", but in real life, I'm 6'4". But all these dating apps are the same thing as just like LinkedIn. The moment you find true love and get off the app, they can't take money from you anymore. So why would LinkedIn have a vested interest in getting you a job? LinkedIn is nothing more than a website to search and see where jobs are, and then you go to that website and apply. Just to give you a frame of reference, the job I got for lying on my resume, I applied to on LinkedIn 3 separate times. It wasn't until I applied on the actual website that I got a call back. So LinkedIn, Indeed, these are places where applications go to die. It is nothing more than a research hub, and on its worst day, it's a place where some grindstep sigma beta ass dude who just proposed to his girlfriend wants to talk about why him crushing his sales order led to him being able to propose to his girlfriend and why you need to grind harder. It is a place where people go to become more depressed, because whether you like it or not, your depression means that you still have to keep coming back to them. So I think absolutely you should remove yourself from this, and it's just going to make you vulnerable. Anytime a company has this much access to you, it's dare I say dangerous. We remember, what's that one, Glassdoor? Glassdoor lost its respect when for some reason one day when we all came back to the app, companies could see who said what about their apps. Our names started popping up on people's shit, and I'm gonna just keep it real. I was talking good shit about people on that app. I was talking good shit. So imagine my surprise when people started hitting me up saying, "Hey, can you take down that report, that mean thing you said?" No. You think I'm afraid? I'm too afraid to say it to your face? I'll call you a trash bag person to your face if it's warranted. But this is one of the most serious research, and it's one of the things that I hate the most. People who are trying to pull themselves up by their bootstrap. You hear this all the time from very super conservative people and super like, oh, don't take welfare and social things, don't use them. But when companies are doing weak ass shit like this, it makes you really wonder, like, why should we respect those calls for action when people, like, literally the people who are down bad the most, who need the most help and are trying their best to get themselves back on their own feet and do it in a meaningful way with some dignity, but are literally have the potential to have their information stolen and used against them to keep them in that perpetual ass system. That's some diabolical shit. But that's that. And once again, I'm not accusing LinkedIn of doing this, but that's just the next thought process, because now that they have your data and they're going to sell your data, I mean, it's just a matter of time before you figure it out that you're not getting any work here. So they're going to have to figure out another way to kind of keep you on this app. And I just don't see it as a profitable business plan if your business model is to get rid of your customers. It doesn't work like that. But that's just my thoughts on it. Let me know what you think. Yeah.
Bang, bang, bang.
Like, share, subscribe. You guys know I love your faces. Come on now. Don't let me down. Say some nice shit in the comment section. Oh my God. All right, we're done. Oh, I benched 400 pounds for 2, and the bar landed very awkwardly on my nipples. I'm feeling very tender. Looks like all the cool kids are in chat. What's up? I'm trying to find the settings. Wait, settings for what? Oh, you found the settings? Yeah, yeah. I already turned mine off, but you should absolutely turn it off. if you have the settings. It's super annoying. Wouldn't you want people to do a scrape on your LinkedIn data? It's about data correlation. It's the most powerful tool in the world that is non-violent. No, Omni. Like I was able, like well, I was dating a girl once, and she was, and the thing that bothered me the most about her was like she never like checked her privacy settings. Never checked her privacy settings. Like so her Wi-Fi was wide open, her networks were always open. She just used stuff openly and she didn't care. And I had to tell her like you don't know how easy it is for people to find you. And she was like people couldn't find me. And I literally all I did was pay $10 for a mass clump of data, and I sift out the data, and I found 15 points that literally could predict her cycle based on all the apps she was using. Her cycle, her birthday, if she had pets or not, like what type of pet it was. It's crazy what that metadata can do. Yeah, yeah, brag about it. First place. First place. Where do medical people look for jobs? Medical people look for job. Well, it depends on what your is. Medical jobs are kind of it's kind of twofold. If you have como se dice the certifications, the degrees, um, the specialist designation, then you kind of look for jobs through like where you want to live, because working in hospitals comes down to private or government. If you want a private situation, you're probably gonna have to know somebody. But if you want to work for the government, they'll hire you off the street. I think very much so for the government jobs. Though they have county websites, you can go there. But it depends on what your specialty is, what your skill set is, shit like that. Ayo, Tiogo Viria from YouTube just recommended your stream vertical. Uh, oh, just recommend my stream on YouTube live to me. Nice. Your earlier video about Amazon ending work from home was really neat. Appreciate it. Thank you so much. Yeah, I always do the vertical on YouTube because it functions like what's it called? Like a short, so get a little bit more traction with it. You are correct about LinkedIn. The thing about it is that's the thing I hate the most about it. I hate that I'm correct about it, and nobody's doing anything about it. Did you watch the Oprah gig with Kamala today? No, I didn't. Was there anything of significance that happened? Did anything of significance happen? It was very good. I will say this. During the DNC, Oprah probably had the best segment for day three, other than Tim Walz. Tim Walz. Oprah's segment was really good. Purple jacket and all. Like, she definitely came out there and got the people going. Yeah. Okay. And yo, shout out to me for not plugging in my phone beforehand. Full hands. Uh, I was just asking what the key takeaways were. What was the reason for it? Where was it? Because, you know, with less than 50 days, I think 47 days to go, a big part of their push needs to be talking to people who don't want to vote, who don't know who to vote for, which is crazy to think about, but I know I'm online too much. I'm way online too much. So did a great job showing the issues of the presidential race. I gotta rewatch it. I gotta watch it because I definitely didn't. It didn't register. I didn't even know it was a thing. I know who I'm voting for. Yeah, you know, regardless of who you want to vote for, you just go vote. You know, go check, make sure you're registered because you don't get to complain if you're not participating. Oh, I don't like the results of this election. Shut up. I don't like the I don't like your face. I don't know if I'm upset about Jill Stein doesn't know that she's passed away. She covered No Money to Live, abortion, guns. It was very well done the way Oprah used to run her show in Chicago. Oh, okay. A little bit of nostalgia bait. Nice. Nice, nice. But were these undecided people or were these like people who were decided? Because I would have loved to see her talk to like a single mother of two white woman living in Mobile, Alabama, type shit. The people were people who were in trouble. Omni, okay, Omni, you're giving high praises here. I gotta check this out. Yag, did you see this? Turn the alerts back on. Thank you, Crumb. Thank you. There are no events to display. Election is so close. I can't wait. People are going to go crazy. And the thing about it is just like I'm kind of electioned out. Like I'm just like, okay, I get it. I get it. And I guess like the thing that I was hoping for was for the Republican Party to be different enough that their impact would be felt. But nothing really changed. white in PA who were overstretched when they bought a house. A young lady who needed an abortion and couldn't get one. A young girl who was shot at a school in Georgia. Her dad was an idiot, and Kamala was great with him. Oh my! So she didn't have it the easy way. I'm very curious to see how this interaction went. So she didn't get it all easy. She had some challengers in there. Hey yo, what's up, JK? Fascinating. Yeah, I definitely got to check this shit out. I believe it when I see it. You excuse me for not having much faith in Harris. And what I always say, hey, there's no point in pretending like you don't like somebody you're gonna vote for. Figure out how to. You got to figure out how to come to terms with it, or or make it make sense. But I think like someone said this the other day to me, and I told them like it makes no difference who you're angry about. The only thing you got to do. Good thing I'm not voting for her. No, that's very true. That's very true. But like, yeah, this person was explaining to me why Harris isn't the best choice, and I asked them. So I was like, okay, name a candidate who is a better choice. Then I'm all for hearing your grievances, but I'm not interested in listening to people who don't have. You don't. No one has a better mathematical choice. And then they were like, well, this is how is anything supposed to change if we keep doing the same thing? And I was like, and that's a problem for the next generation to solve. Maybe when I choose to run for president, maybe I can solve that problem for y'all. But like right now, we're under the heel of of a group of people who don't give a fuck, right? Remember all those companies that were like, we got this green initiative. We got this green initiative. Same companies forcing their workers who all have to drive 20 miles surplus there and back to start coming back to the office 100% of the time. Hero Grimy. Grimy don't even like streaming. How am I going to get him to stand in front of a mic and talk to people? One thing you will understand, the abortion law came up discussing a doctor that wouldn't operate on a specific. Okay, and I was saying this too. We had a conversation about this at the hospital, and maybe because we're in a blue state, but any doctor who says that they're afraid to do an abortion because of being arrested that doesn't exist. I have openly admitted how I have stolen money from my insurance company to get people their drugs. Openly. And all I get is a finger wagging. Because who's going to work the night shift on Friday that I signed up for? Didn't think so. And we just saw, I think there's some DA or somebody has pressed charges against a doctor for abandoning their patient, which is what it is. There are hundreds of laws that would make some doctors' jobs impossible. But you took a oath to save lives first, ask questions later. Period. And barring someone physically stopping you, you should always try and save life. So everyone else thought the doctor was afraid of jail, law, or being fired by the board. And there's a doctor actually in Florida. There's a doctor actually in Florida who wrote an op-ed in a New York newspaper talking about he's done like 30 abortions since the law went into effect and no one has come knocking on his door. It's because no one really cares about this shit. It's just a talking point. An unfortunate one, but it's definitely a talking point. Kamala didn't do much as VP either, so he's perfect for the job. Hey, yo, one, I'm not gonna let you disrespect Grimy like that. You could disrespect Kamala all you want, but you're not gonna do that to Grimy. As Satan said, stupidity is doing the same thing over and over again. Yeah, something different will happen. Yeah. I don't know. I understand we can discount her, but unfortunately, she's what we have. Back to learning how to write good code. No, Omni, it's more than she's not. She's not just an ultimatum. I think we have the capacity with her to do a lot of good things, but we need to remove the crutches of the Democratic Party, which is never having control of the Senate and the House without having any deflectors. Like, we need to have a strong majority in those places so we can actually do things representative of the people. Kamala is easily the best candidate that I've seen running, maybe next to Bernie. Like, she's definitely the most progressive, but I can't, like, it's one of those things where you have to put her under the microscope, and a lot of things that I care about, she's not going to solve them. A lot of things that people care about, she's not going to solve them. But one thing she can do in what the Democrats love to do in these situations is be a band-aid for the situation we're in. And it sucks, but that is how the cookie is going to crumble. And I don't think it doesn't hurt us to acknowledge that we want more and expect more from her type shit, you know? Well, yeah, because the Republican Party's worst fears is a group of people getting far enough that they don't have to struggle. When Republicans and Democrats, when people aren't struggling, it removes that codependency that they need on them. Republicans use it differently than how Democrats use it, but they both use it alike. Republicans use it to garner fear. The reason why you're poor is because of the black Haitian people. Democrats, the reason why this system isn't working out is because of the racist. They're both wrong, but they're both talking about an issue. So there's enough truth in it. There's enough truth in both statements, but the actions that are being taken in order to fix the root cause analysis is never going to be taken. And once you solve the root cause analysis, then this problem goes away. And when you grow up shorthanding with them T-Rex short arms, you as a person then start to emulate that same behavior. You know one behavior my parents exhibit that disgust me is when it's time for a bill or something like that to come out. They start looking around to see who's gonna pitch in. Look, if I invited my family, like I'm taking my family out to dinner, I'm not asking nobody to pitch in. If you want to pitch in, that's on you. If it's me, my brother and sister, the heads of the family, if they want to pitch in, that's great. But if they don't pitch in, well, I didn't ask you to. I invited you here to eat. I didn't invite you here to pay a bill. Like, we would always have to do some event where we couldn't thoroughly enjoy ourselves because everyone couldn't enjoy themselves at the table. And I just said, if you have enough to make sure everyone enjoys themselves, just do it. Don't make it weird. Yeah, people aren't neighborly. People look at each other and say, my grass is better than yours. Like, guys, like, we all do it in some sort of way. Hey, more donuts. I've never seen a person angry eating a donut. Just give us more donuts, man. Oh yeah. So I gotta look at the PR that how do you accept PRs and shit like that? We got one fork. We got a pull request. Adding test. Yeah, I'm looking at the GitHub now. Tani sent it to us yesterday, so I'm gonna pull it. It doesn't look like she messed with any of the code originally. Squash and merge, rebase and merge. The one commit from the branch will be rebased and added to the base branch. The one commit from this branch will be added to the base branch. I think the create a merge comment. All comments from this branch will be added to the. I think that's what we want. Thanks. I will try and make this make sense to me. All right, so it's merged and we've committed. Oh shit. How do we? Ooh. Oh, okay. So I have accepted. All right. So now we can go here, and we can go and we'll get pull. We'll get pull everything, and then we'll see what she added. Hey, yo, what up, Ran? YouTube has been popping off, y'all. We broke our view. We broke our hours. Our hour. I don't know how to say this. Like the most hours viewed in one day. So we got up to 1,000 hours watched in one day. Never accomplished that before. 34 new subscribers on YouTube. We've been popping off, y'all. Clap it up. Golden Salmon. We are making a BST tree that we can use. Get pull. A BST tree that we can use to search through a tree and then put all the Naruto characters in alphabetical order. We're basically learning how to do like binary stuff or binary search trees because chat said I had to learn it. I had to learn it once. I had to learn how to do it once, but then after that, my job was responsible for making sure they teach me. All right, so we got the get pool, main test, npm test. Okay, npm. Wait. npm run. Okay, so we have the run package here, and all the registries are true. And she uses jest instead of test, so her test does work. Huh. Let's also read what she wrote in the Discord. We had to spice it up because Golden, we had to spice this shit up because it was so boring. Oh my goodness. Like, it was painfully boring. So we had to spice it up a little bit. Alright, so Tani said a recommendation don't have a separate build tree function. Do it on the fly instead. Example, tree.node. Expect tree.node. It should become tree node, tree root name, tree to be, Naruto true to be. It's already balanced. It's already a balanced tree. You first create an empty tree. Empty trees are balanced by definition. You add one, it's still balanced. You add two, it's still balanced. You add three, then you immediately rotate the second one, tree still balanced, etc., etc. So the illusion that I thought of making the tree balanced was probably the thing that was hurting me here. Yeah, we'll let Tony handle the rest of this. Let's see what else we got on the checklist. I am perfectly fine moving on from this. Next time she's here, we're gonna ask her. Yeah, Rain, you're absolutely right. I do want to get this done because it's been 3 days. We're over this shit. uh, and the good thing is, someone in the chat knows how to do it, so we can move on. And and we got work to do, and we got a busy weekend. We're not gonna have a lot of time to. Well, it's not that it's not working. It's just not working to my imagination. I had the idea that like it would actually show me how it searches through it, but in reality, it happens that the function and everything I'm writing does it. There is no, you're not gonna see it, bro. Like, there's no visual for how this data is sorted. You can see the visualization of the tree if you use the prettier method, but my mind thought I was going to see the results. In reality, I'm writing the function that will make the thing that I want to see happen. That's all. That's all I'm doing. What part do you not understand? I think it's not so much understanding. It's more so like, once again, I was expecting a visual representation of what I did. I didn't get that. So you see how like I made this map? I thought like I would get some end result that would give me this tree, but it's not. That's not what is going to happen. I can do it with the prettier method, but I essentially built a tree that was already balanced. Yeah, that and I think that's the gist of it. Like I don't have a reason in my programming at my programming level to implement something of this capacity or of this caliber, right? I don't have that. So for me, I'm like, okay, we got it. We did it. It's sort of like the linked list and the hash map. I don't have there's nothing in my code that could use that today. So I'm not fighting with it. The depth first search and the breadth first search? No. Maybe I am, but I don't know it by that term. I don't know those terms. Yeah, because the next project is this. They're the only one. There is only one term for those. Okay. Um, what you call that? Depth first. Depth first search. Do do do. Oh wait, my music is my music playing? Damn, my music ain't playing. The disrespect. But on Tinder, I'm 6 feet.
My baby don't mess around because she loves me so, and yes I know for sure. But she really wanna, but can't stand to see me walk.
Depth first search. Depth first search for a graph or similar. Hey, yo, get out my way. Depth first travel. The only catch here is that unlike the tree graphs, may contain cycles, a node may be visited twice. To avoid process a node more than once, use the Boolean and visited array. A graph can. I don't know what the hell this graph shit is, but someone told me that was the more advanced version. This one has graph in it too. I don't know. Yeah, Omni, put something in the Discord. Put it in the please put it here section. Find me the perfect example, and then we can go from there. What is this? Now you're a pro at DFS. I am not a pro at DFS and BFS. Let's try using our search algorithm on a real problem. Okay. For this project, you'll need to use a graph. Oh shit. A data structure that is similar but not identical to binary tree. For a good introduction on what graphs are, search DFS tree. I don't think I'm gonna have a good time with this project. This is probably the first time in the Odin project that I do not feel like these mother lovers were cooking. Unlike a linear data structure array, linked to a list of queeks and stacks, queues, which have only one logical way to travel from the tree. Generally, there are two widely used ways to traversing trees, DFS and BFS. What is DFS? DFS is a technique used to traverse trees or graphs. Here, backtracking is used to used for traversal in the traversal first. In this traversal first, the deepest node is visited and then backtracked to the parent node if no sibling of the node exists. Okay, I think I remember this. Zero, one. Unless it has a child, so then it goes 0, 2. Back to 0, then it goes to 3. 3 goes back to 0. Then it goes back to 1. Then 1 goes to 4. 4 goes back to 1. 1 goes back to 5. 5 goes back to 1. 1 goes back to 0. 0 goes to 2 to get to 6. 6 to get to 2. 2 to get to 0. 0, 3, 7, 7, 7. Okay. I thought it should be 1 to 4. I thought the output should be 1 to 4 too. It should be 0, 1, 4. 5, 2, 6, 3, 7. Just what you have. So somebody lying. Somebody lying. I thought so too, but I wasn't. Who am I to tell the website they wrong? I'm learning. Or wait, maybe they fixed it here. In order, 4, 2, 5, 1, 3, pre-order, 1, 2, 1, 3, 3, 1, 4 1 2 4 4 2 4 2 4 2 1 3. No, 1 2 4 2 5 2 1 3. So it's just 1 2 1 2 4 5 3. So pre-order, that's right. And then post order 4 5 4 2 5. So 4 5 2. So 4 5 2 3 1. 4 5 2 3 1. Okay. The problem with the graph is you can have cycles. Be aware of cycle problems and think about how it makes the graph different from the tree. The cycle is a place where you can get to the same place in more than one way. This most simple cycle is a triangle with 3 nodes. Interesting. How am I supposed to implement this into a fucking chess game though? I gotta move a knight on a chessboard. We gotta use a lot of old skills. We're gonna be using the grid. We're gonna need a JavaScript for pinpoint. We're gonna need some hover points. This shit's about to get intense. If you have a binary tree with 3 nodes and you draw a line between the 2 nodes, you would get a simple tree node. Well, shit. They want us to do the graph method for this. They're already telling us you gonna use the graph method. So let's see what Khan Academy has to say about this shit. Oh my god. They got shits in circles. What is going on? What is this? Oh. This is not something you should be taking lightly.
Where do we get it by?
For several weeks in college courses, so be ready for a lot of work. Man, I lied on my resume. I've been working. I've been working. Okay. What do they want from me? I wonder if there's a mathematical equation for this. There's got to be a video on this. And we're not talking about like a boring video either. What's the word I was thinking of? DFS graph. feel like you can't teach this in 4 minutes. But I also don't want to be here for 20 minutes. I gotta learn about the graph first. It's funny because I was thinking the same thing looking at Khan. I was like, man, this is some bullshit. The social net, like, because they want to use an example. Don't forget to look at the section on representing graphs. Alright, at least I can save this one. I'm pretty sure there's something out there. And you know what? Tomorrow I gotta go get my car to pass that to take my car to that emissions test thing. So I'll have a lot of downtime to really look into this. Okay. Introduction to graphics on YouTube. That is a complex animal. You need to know the tree is different from a graph. A graph is generalization of a tree. Oh. They let the episodes out for JJK today too. So you saying what? The introductions to graphs for data structure? I like this one for some reason. The picture captivated me. Oh shit.
Into the vast and incredibly interesting field of graph theory from a computer science perspective. Here's an example of a type of graph that we're going to talk about extensively in this video. If you were to ask me what's the simplest definition of a graph for someone who knows nothing about the field, what I could tell you is that you can think of a graph as a network that helps define and visualize relationships between various components. In this example, the circles that you see represent The components and the lines connecting them can be thought of as signifying a relationship between the components. These ideas, of course, have more formal names in graph theory. We refer to these circles as vertices or nodes, and the relationships signified by connecting lines represent what we call edges in a graph. Graph theory is all about the study of the properties of these types of networks and how they can be used to model and solve a whole host of interesting problems. This video is all about introducing you to core concepts related to graph theory that we will then use to study fundamental graph algorithms. We'll first start with an important discussion on why we should even care about studying graphs, after which we'll formally define a graph and introduce important terminology used to communicate ideas about graphs. Then we'll talk about how computers might represent graphs as a data structure. And then I'll finish the video off with some interesting problems and questions around graphs that you can think about going forward. Let's first start with the most important question. Why should we care about graph theory? And the short answer to this is graphs show up everywhere, sometimes in expected ways and also sometimes in surprising ways. One of the most direct applications are in mapping and navigation applications. In any of these applications, you often deal with roads and intersections which can be naturally modeled as a graph, where each vertex represents an intersection and the edge between vertices signify the roads between intersections. You could imagine navigation applications might be interested in the best route between a starting point and an ending point, and this problem naturally translates into many well-known graph theory problems. Another natural application of graphs is in social networks. In the context of this application, imagine edges of a graph now represent friendships between people in a network, where each node now represents an individual. Suppose you are interested in recommending new friends.
I don't know, but this music really has my attention.
Currently has 4 friends. A natural way to solve this problem is to look at all of person A's friends, find friends of these friends, and recommend them. These type of problems are easily modeled and solved with graph theory. So these are examples of applications where it's honestly not too surprising that something like graph theory shows up, but the neat thing about graph theory is that it also finds ways to show up in the most unexpected places. Let's talk about Sudoku. That's right, I bet you didn't see that one coming. A lot of you have probably encountered a Sudoku puzzle at some point, but for those of you who haven't, here's a quick summary of how this puzzle works so we're all on the same page. The goal of Sudoku is to fill missing entries of a 9x9 grid with numbers 1 through 9, but with a few constraints. The first constraint is that each 3x3 subgrid cannot have repeated numbers. The next constraint is that each row must have unique entries, and the last constraint puts a similar limitation on the columns in which all entries of a column must be unique. So it turns out that computers can solve Sudoku puzzles on the same page. The goal of Sudoku is to fill missing entries of a 9x9 grid with numbers 1 through 9, but with a few constraints. The first constraint is that each 3x3 subgrid cannot have repeated numbers. The next constraint is that each row must have unique entries, and the last constraint puts a similar limitation on the columns in which all entries of a column must be unique. So it turns out that computers can solve Sudoku puzzles efficiently using graph theory. The graph here is quite subtle, but it does exist. What we're going to do is we're going to assign each number a color.
You said, notice that the friends problem is actually a couple of trees back to back. This is how graphs are similar to trees. Oh. So graphs incorporate trees, but they're not trees.
And then construct a graph as follows. For each 3x3 grid, we'll fill out the unknown entries with the respective color for that number and assign one color to all unknown entries. The constraint here is that all of these 9 nodes as a group must have unique colors. We can then extend this mapping to all other 3x3 grids and create the following graph. Now we still have to take care of the other constraints. We can connect the graph along each row to represent the idea that every row in the graph must have a unique color, and we can do the same connections along columns for that respective constraint. Now we have a graph theory problem where we attempt to find colors assigned to vertices that satisfies all the laid out constraints. And turns out that this is actually a well-known graph problem that graph theory provides an elegant algorithm for, and once we find a set of colors, we have a solution to a Sudoku puzzle. Let's now proceed to formally define a graph. A graph is a set of vertices and edges where each edge is a connection between vertices. The way we usually denote an edge in a graph is by referring to it as a pair of vertices. And as mentioned before, vertices and nodes are just different names for the same concept that we will use interchangeably when discussing graphs.
Say that shit again.
The way we usually denote an edge in a graph is by referring to it as a pair of vertices. And as mentioned before, vertices and nodes are just different names for the same concept that we will use interchangeably when discussing graphs.
I heard what you said, but what?
Let's now proceed to formally define a graph. A graph is a set of vertices and edges where each edge is a connection between vertices. The way we usually denote an edge in a graph is by referring to it as a pair of vertices. And as mentioned before, vertices and nodes are just different names for the same concept that we will use interchangeably when discussing graphs.
Okay.
If you are forced to mathematically write down a definition of a graph, we can use set notation. For this particular graph, the vertex set looks like this, and our set of edges would be denoted with this notation. Let's now define some important terminology that you'll see over and over again when talking about graphs. The first important term is the concept of neighbors in a graph. Formally, two vertices are neighbors if an edge connects them. Here's an example. Vertices 1 and 8 of this graph are neighbors since they are connected by an edge. One thing that we will often query a graph for is all neighbors of a particular vertex. For example, if we were to ask for all neighbors of node 0, the result would be the following set of 3 nodes. Nodes 4, 6, and 8. A related concept is the degree of a vertex. A degree of a specific vertex is equal to the number of edges connected to that vertex, or equivalently, the number of neighbors. As per this definition, the degree of vertex 0 would be 3, and the degree of vertex 3 would be 2. Let's now talk about paths. Paths are simply defined as a sequence of vertices connected by edges. Most of the paths that we deal with will be paths with unique vertices. For example, one path from vertex 0 to vertex 2 is shown here, and all vertices in the path only show up once, which is what we will assume most of the time. One feature of paths is that they have respective lengths. A path length is simply defined as the number of edges in a path. In this example, the path length we have here would be 4. A related idea to a path is the concept of a cycle. A cycle is defined as a path that starts and ends at the same vertex. One key note about cycles is that all cycles are paths, but not all paths are necessarily cycles. There are several cycles in this graph. Here's an example of a cycle that begins at vertex 0 and ends at vertex 0. The last term I want to talk about is the concept of connectivity, which can be used in several contexts. The first context is with respect to two specific vertices. Two vertices are connected if a path exists between them. The second context you may encounter connectivity is when it is applied to a general graph. A graph is connected when all vertices are pairwise connected. In other words, a path exists between all pairs of vertices. This graph is an example of a connected graph since if you pick any two vertices in the graph, we can identify a path between them. However, if we change up the graph a little bit, we now have an example of a graph that is not connected. Now it's easy to see that no path exists between several pairs of vertices. This naturally leads to a third context that connectivity can be applied, which is the idea of a connected component. A connected component is a subset of vertices of the graph that is connected. For example, in this graph we have two connected when all vertices are pairwise connected. In other words, a path exists between all pairs of vertices. This graph is an example of a connected graph since if you pick any two vertices in the graph, we can identify a path between them. However, if we change up the graph a little bit, we now have an example of a graph that is not connected. Now it's easy to see that no path exists between several pairs of vertices. This naturally leads to a third context that connectivity can be applied, which is the idea of a connected component. A connected component is a subset of vertices of the graph that is connected. For example, in this graph we have two connected components, the first being the following set of vertices, and then the remaining vertices of the graph form the second connected component.
Okay.
Let's now transition to the types of graphs that you may encounter. The main graph we've seen so far is specifically called an undirected graph, where, for example, if I have an edge connecting vertex 0 to vertex 1, it's kind of implied that I also have an edge from vertex 1 to vertex 0. A graph where this would not be the case is called a directed graph, where now edges are unidirectional. Directed graphs also have their own classes. This particular graph has a cycle, so we can be more specific by referring to this graph as a directed cyclic graph. On the other hand, if a graph is directed and contains no cycles, we refer to that specifically as a directed acyclic graph, which is a specific subset of graphs that has been studied quite rigorously since they show up in all sorts of interesting problems. Another important graph is a weighted graph. This graph is unique because each edge is now not treated equally, and some edges might have a larger weight than others. This can naturally model interesting metrics like traffic distances on maps and many other ideas. Another important class of graphs is trees. Trees have three key properties. All trees are connected and acyclic. Removing an edge from a tree will disconnect the entire graph, and furthermore, adding any single edge to a tree will create a cycle. These are three valid examples of trees, and I encourage you to take a second, pause the video, and confirm that all these properties hold. Personally, I find verifying the second and third properties surprisingly satisfying. Really emphasizes how fragile a tree structure is, which I think is
Connected and acyclic. Removing the edge disconnects the graph path. Removing the edges of any of these between 0 and 1, 0 and 2. Or are they talking about in everything? Hold on 1 second. PRs. Control F. True. Hold on. This is well done, but moves very. Yeah, it moves at a breakneck speed. I'm still trying to figure out, like, I wish they had showed more examples of how trees become friends, but they lost me around the 6-minute mark. The music is very enticing though, but I feel like I'm learning through osmosis. I know that won't satisfy the situation, but we'll go through this a few more times. Ah, shit. Yeah, I can see it. Yeah, I can see the tree, but like the rules that I was stating, 0102 breaks it up. The tree on the right is drawn with the root of the tree in the middle, which is a little confusing. but it makes sense to me because I can see the two children on the outside. The parent's it's a parent of 4 instead of a parent of 2. The question is, in the linear one, who is the parent and who is the child? Are all of those parents? Are there 4 parents connected to each other? Or one parent and 3? But no, because then there's 3 parents and one. I don't know. It's the first one that's confusing me. I'm Googling it. Turn PR on. Finish. 0 is the parent of 1, 1 is the parent of 2, 2 is the parent of 3. So 4 is the only true child? Oh wait, there is no 4. So nodes can hold 2 different classifications? Yatta. It's doing 5 head stuff, and I feel like I need at least 2 brains. But we seeing it. We seeing it.
It's kind of cool.
How you doing, Nah?
Let's now move on to some more hands-on ideas. How does a computer represent a graph as a data structure? Take, for example, the following graphs. How would you go about organizing the information in this graph on a computer? Turns out that there are several accepted ways to do this, and some of them are better than others depending on the context. The first idea that is quite natural is to map vertices to one another through a matrix, which we formally call an adjacency matrix. The
Hey,
rules
that's a
for creating
checkered
this
board.
matrix are fairly intuitive. If an edge between node I and j exists, we will indicate this with an entry 1 in our matrix. Otherwise, the entry will be 0. Following these rules, this is what our adjacency matrix looks like for this graph. Notice that each edge creates 2 entries since this is an undirected graph. Make sure you take a moment to understand the mapping.
So 0 to 0 is 0, 0 to 1 is 1, 2 to 3. Oh wait, 2 to 4. There is none, so it's a 0. 4 to 3. 4 to 3, there is 1. 2 to 3, there is 1. There isn't one from... What? There's not one for 2 to 1? No, there isn't. Holy shit, but 0 to 3 is possible. Damn, son. Yo, it would be dope if they could put one in the middle. Then that way you had like a breaker point that could touch all of them, making it even faster. But wait, yeah, because if you wanted to go to 3, actually no, it would be the same distance. 0, 1, 3. 0, 1, 3. Well, no. I guess it's the same travel distance. Never mind. Never mind. Nan, how you doing? I can't see any of my alerts. I don't know if my alerts are... I know they're on, but my mini feed has been cleared out. Yeah, I'm more human than human. Getting sleepy. No. Come on. We gotta stay up. We gotta stay focused. Go.
We have here. The second valid representation of a graph is actually
We're off tomorrow, but we have to go get our emissions test tomorrow. Hopefully that shit work.
fairly simple. We take all the edges and construct a set with each edge as follows. This representation is called an edge set, and it also contains all the information about vertices and edges that you would need for a graph. However, this representation is not as common because it's a little hard to extract information about vertices of a graph using this particular representation.
It is really good sleeping, but I like it, so I'm not
The graph
sleepy.
is called an adjacency list, and this is actually the most common representation used. The idea works as follows.
So it sounds like with that knight chess piece, I'm gonna have to map out all the possible places it could go. I would have to map out all the possible places it can go and map out how to reach it on that board. I've never played chess before, and whenever I do, I always play with the one that highlights the places I can go. I feel that gives me a strategic disadvantage.
We take each vertex and map the vertex to a list of its neighbors. For example, node 0 has 3 neighbors, specifically nodes 1, 2, and 3, so we map it to a list containing those values. The rest of the list is constructed in a similar manner. The nice thing about this representation is that it gives us an easy access to neighbors of a particular node, which is a tool that will be immensely useful in graph algorithms. Furthermore, this representation exploits the fact that most graphs in the real world are going to be sparse, meaning that we have a large number of vertices with each vertex having relatively few edges. For example, in a social network, it would actually make the most sense to have this representation since there are going to be billions of nodes, but each node is unlikely to have more than a few thousand edges. An adjacency matrix for a graph like that would take way too much memory, but with an adjacency list, it's much more manageable. For this reason, in future videos, we will primarily use adjacency lists as a way to...
But yeah, so that was my whole thing. Like, so you put it in an array, you put all the possible movements of an array in an array. Maybe you label them, I don't know. But once you have them in the array, or, oh, actually, because it's on a board, the spot on the board is the possible array. So if they are on a spot, you can then tell based on where they are from how far you are if the move that they're trying to make is possible. I don't know, that's weird. This is hurting my brain.
Represent graphs. The final thing I want to do in this video is to discuss some of the interesting problems and questions you may find in graph theory. In future videos, we'll show you how you can apply graph algorithms to solve many of these problems. A fairly standard problem that you'll likely encounter all the time revolves around connectivity between two vertices. For example, It's easy for us to see that vertices 0 and 3 have many paths between them, but what sort of algorithms can we use to allow a computer to efficiently solve this problem? We can naturally extend this problem to ask if an entire graph is then connected. There are a variety of efficient algorithms to solve these problems that we will cover in the next few videos. Another interesting problem in graph theory is the shortest path problem. Specifically, what is the path of the least length between two vertices? For this particular graph, here's the shortest path between vertices 0 and 3, which is something we as humans can generally eyeball for small enough graphs, but once again, what's the algorithm to solve the problem generally? Then there is a problem of cycle detection in a graph. Many of the algorithms that are used for connectivity problems can be naturally adapted to solve this problem as well. Another interesting problem in graph theory has to do with vertex coloring, which we actually saw in the Sudoku example. The problem formally stated is, given a set of colors, can we assign a color to each vertex such that no two neighbors are assigned the same color? In this graph, for 2 colors, no such solution exists, but if given 3 colors, this problem has a solution.
Wait a minute, what? If you made this one blue, black, blue, black, blue. Oh shit, you're right. Blue, black, blue, black. Yeah, that would still be blue shit.
Another very interesting problem to ask about graphs is whether a path exists that uses every edge exactly once. This might be harder to tell, but this graph does indeed have one of these paths, and an efficient algorithm for this problem exists. These type of paths have tons of interesting applications in bioinformatics and circuit design. A similar question that you may ask is, what about the existence of a path that uses every vertex exactly once? Such a path also exists in this graph, but I think what you'll find more surprising is that there exists no efficient algorithms to solve this problem. What I mean by that is that all algorithms that we have so far run in exponential time for this problem, which is incredibly slow for large enough graphs. In fact, if you are able to find an efficient algorithm for this particular problem, you would probably be given every single computer science award in existence because it would help resolve a long-standing open problem. But don't. A similar question that you may ask is, what about the existence of a path that uses every vertex exactly once? Such a path also exists in this graph, but I think what you'll find more surprising is that there exists no efficient algorithms to solve this problem. What I mean by that is that all algorithms that we have so far run in exponential time for this problem, which is incredibly slow for large enough graphs. In fact, if you are able to find an efficient algorithm for this particular problem, you would probably be given every single computer science award in existence because it would help resolve a long-standing open problem. But don't get your hopes up there, because there's a fairly large consensus that no efficient algorithm for this problem exists. Let's now take a moment to recap the big ideas.
I don't even know what the problem is.
We first introduced graph theory through a variety of cool applications where you saw why someone should even study graph theory. We then formally defined graph theory along with important terminology and types of graphs that you will encounter. These concepts are incredibly important to understand so that we have an appropriate framework for discussing graphs. We then introduced several representations of a graph as a data structure, with the specific emphasis on the practicality of the adjacency list. And lastly, we introduced some diverse and interesting problems in graph theory to motivate the algorithms that we will go through in future videos. I hope this discussion gave you an appreciation for the massive field of graph theory. It's definitely one of my favorite topics in computer science, and I hope it becomes yours as well. Thanks for watching me, and as always, I'd appreciate it if you hit the like button. If you If you want to see more content like this, be sure to hit the
This is really good. It's not bad for my first foray into this. Am I colorblind? No, I'm dyslexic. But yeah, back then when I say blue, black, blue, it's just how we count things in the medical field. If it's not blue, then it's black. My son, I got laid off. I'm sorry to hear that. What's the next move? You know we don't stay down for long. What is the next move? Yeah, but we're in hiring season. The Feds cut the rates 0.5. We got 3 more meetings from Papa Powell. The rates will continue to be cut. Inflation is getting down closer to 2.0. Election season's 47 days away from being ready. It's not the worst time to interview. You can still get it in before November. Interview now, get the offer letter. Offer letter before November is definitely possible. Got a whole month. What you talking about? And it looks harmless at first sight, but it's definitely a lot of moving parts.
In this video, we will take a look at our first graph algorithm, depth first search, or more informally DFS. This algorithm is one of the most fundamental algorithms in graph theory, and many of the ideas in this video will carry over to more advanced graph algorithms. For that reason, in this video, I'm going to spend some extra time building intuition for the ideas behind this algorithm. Here's what you can expect to get out of this
Exactly,
video.
Omni.
We will first introduce the concept of a graph traversal and what that even means. Then we will try to build our own graph traversal method and show how it intuitively leads to core ideas of depth first search. Once we have an idea behind what depth first search is trying to achieve, we will then spend some time going through the implementation of DFS.
Put it in the please put it here section.
And then we'll finish off this video with some really cool applications of depth first search that I'm sure you're not going to want to miss, so make sure you stick to the end of the video. Let's get started. Given a particular graph, one useful ability involves starting at a single vertex and finding a way to get to every other vertex of the graph. The formal name for this ability is a graph traversal, which is simply defined as an algorithm that visits every vertex of the graph. There are several graph traversal algorithms, and they are primarily differentiated by the order in which they visit vertices. In this video, we will focus on the DFS ordering. So now that we know the basic idea behind a graph traversal, let's take a step back and see if we can sort of invent our own graph traversal. The line of thought that I'm going to present here is actually exactly the DFS algorithm. The goal here is to show you how the DFS algorithm is really a surprisingly intuitive idea, something that with some thought, you probably could have come up with on your own. Let's take a crack at it with this graph. Given a start vertex, we want to find an order that we can go through the vertices of the graph so that we guarantee that we end up visiting every vertex. Let's start with vertex 0. From vertex 0, we have a couple of options for how we might want to continue. The option we choose doesn't really matter too much here, since our hope is that we'll eventually explore all the vertices anyway. Let's say that we choose to visit vertex 1 from here. What now? Well, now that we're at vertex 1, we have a new set of choices for where to go next. It doesn't really make sense for us to go back.
Oh, you guys don't see the graph?
Since we've already seen it. So let's pick a new vertex to explore. Let's go with vertex 2.
Oh.
And from vertex 2,
I was covering
we have a couple of options, namely going to vertex 0 or vertex 1. But we've already seen those vertices, right? So what we might naturally do is say, okay, there's nothing here, since our hope is that we'll eventually explore all the vertices. So now that we know the basic idea behind a graph traversal, let's take a step back and see if we can sort of invent our own graph traversal. The line of thought that I'm going to present here is actually exactly the DFS algorithm. The goal here is to show you how the DFS algorithm is really a surprisingly intuitive idea, something that with some thought, you probably could have come up with on your own. Let's take a crack at it with this graph. Given a start vertex, we want to find an order that we can go through the vertices of the graph so that we guarantee that we end up visiting every vertex. Let's start with vertex 0. From vertex 0, we have a couple of options for how we might want to continue. The option we choose doesn't really matter too much here, since our hope is that we'll eventually explore all the vertices anyway. Let's say that we choose to visit vertex 1 from here. What now? Well, now that we're at vertex 1, we have a new set of choices for where to go next. It doesn't really make sense for us to go back to vertex 0 since we've already seen it, so let's pick a new vertex to explore. Let's go with vertex 2. And from vertex 2, we only have a couple of options, namely going to vertex 0 or vertex 1. But we've already seen those vertices, right? So what we might naturally do is say, okay, there's nothing further we can do from this vertex, so let's take a step back to where we came from, which is vertex 1. And from vertex 1, we now have 2 unexplored vertices that we can then go to. Let's go to vertex 3. From vertex 3, our path forward is pretty set in stone. The only unexplored node is vertex 5, so let's go there. From vertex 5, we have a few options on how to continue traversing the graph, and let's go ahead and pick vertex 6. At vertex 6, we've now reached another dead end similar to what happened with vertex 2, so let's retrace our steps back to vertex 5. From vertex 5, let's say we pick vertex 7 as the next node we visit. From vertex 7, the only path forward is to vertex 8, and from there, we again have only one choice leading us to vertex 9. At vertex 9, we've now hit another dead end, so let's go back to vertex 8. Now what's different this time is that from vertex 8, we have already explored everything there is to see, so let's retrace our steps once again. We got to vertex 8 from vertex 7, so let's go back to there. From vertex 7, we have the same story, so we go back to vertex 5. And everything from vertex 5 has been fully explored, so from vertex 5, we now go back to vertex 3, which was the vertex that got us to vertex 5. Same story here, so let's take one more step back to vertex 1. And now that we are back at vertex 1, we have finally found a new undiscovered vertex. So we now visit vertex 4. From vertex 4, there's nothing new to explore, so we go back to vertex 1, which now also has nothing more to explore, which finally leads us back to vertex 0, which now is also completely explored. And now that we're back to where we started, that's how we know we have traversed every vertex of this graph. So I know that was a lot, but the philosophy of how we explored this graph, but continuing to explore new vertices as we see them until we hit a dead end, is what depth first search is all about. When performing depth first search, think of yourself as a bold and adventurous explorer. Where every
thank
time
God.
you see a new vertex, you will continue to explore new vertices until you hit a dead end, in which case you'll retrace your steps and continue exploration. It's worth noting that there are actually several valid depth first search orderings.
This is the difference between covering the vertices of a graph and covering the edges of the graph.
Familiarization and practice with the core idea behind DFS
Are not
highlighted.
highlighted.
Can generate another ordering by
So
just
basically,
changing
one
the
of them
choices
is
of
you
vertices
can
to
touch
explore
them
whenever we have a choice
without
while sticking
crossing
to the
all
core
paths to get to
philosophy.
them. So there might be
Let's
multiple
start again
paths to
at
get to them,
vertex 0,
but you
and
don't
now
need
we
all
have
of
a
them to
choice
touch
between
them.
choosing vertex 1 or vertex 2 as the next
Interesting.
node to explore.
Shout out to
Let's
Kami
pick
for the
vertex 2.
follow.
Last time we went through this, if you remember, we picked vertex 1. Again, I want to emphasize that both of these choices are valid, and if you were ever asked for the DFS order on a test or an exam, the instructions must be clear on how to make these choices. A common way to do this is to enforce the constraint that you must always pick the node with the smaller value when you have a choice. In that case, we would have picked vertex 1. Anyways, back to what we were doing after visiting vertex 2, we only have one choice, which is now to go to vertex 1. From there, let's say we now visit vertex 4, which then leads us to a dead end, so we go back to vertex 1. Now the path forward leads us to vertex 3,
So then it would be
which
3,
then
5,
forces us to
6,
visit vertex
6,
5,
5,
where we
7,
now have several
7,
choices.
8,
Let's
9.
pick vertex 8 this time. From there,
Oh,
we'll
what?
choose to explore vertex 9, which leads us to a dead end, so we go back to vertex 8. The next vertex we then explore is vertex 7, which leads us to another dead end, so we go back to vertex 8. There's nothing more to explore from vertex 8, so we go back to vertex 5. From vertex 5, we then explore vertex 6, which is the final vertex of the graph that we haven't seen, so that completes another possible DFS ordering. Let's now talk about implementation. It helps to try figure out the implementation on a smaller graph since it has fewer moving parts. Here's one valid DFS ordering for this
And what's
graph.
a cycle again?
One thing that you may have noticed about this process through the examples that we've done so far is that it's actually naturally recursive. We start at a particular node, and once we visit that node, it's almost like we can ignore that node in the graph and run DFS on all of the neighbors of that node. So this inspires one initial idea for how we might implement DFS. Given a particular graph G and a starting vertex V, we first visit V. Then for each neighbor of node V, we can run DFS on the graph with that neighbor as the new starting node. Remember that we are representing graphs using adjacency lists, so an operation like finding the neighbors of a node is quite simple. So let's try the first attempt at an implementation and see what happens. We start at vertex 0, and let's say that the first neighbor we end up picking is node 1, so that's the next node we visit. We then go through the neighbors of node 1 and repeat the process. But there's one big issue with this implementation. Take a second to see if you can figure out what the problem is. The issue...
Watch your mouth. 01 34 342. 0132 0132 023112 013.
Here is that when we iterate through node 1's neighbors, one of those neighbors is node 0. This means that with this current implementation, we'll end up calling DFS on node 0 once again, which would create an infinite cycle of recursion. So how can we fix this? Well, what we want to do is ideally only call the DFS function on nodes that we've never seen before. One way to do this is to essentially mark nodes that have already been visited. We can do this by maintaining a list of Boolean values where each one is mapped to a vertex of the graph. Initially, all these values will be false since we haven't visited any vertex. But as soon as we visit a vertex, we can mark the vertex as something we've seen before by changing the respective index to true. Now with the vertices marked appropriately, we can now call DFS recursively on a vertex if that vertex is not currently marked. Let's dig a little bit deeper to verify that this implementation actually works. We first call the DFS function on our graph with starting vertex 0. This will then visit vertex 0, giving us the first vertex of our traversal. After that, we mark the vertex and begin looping through the neighbors of vertex 0. Let's say the first vertex from our neighbors we look at is vertex 1. What happens now is that we make a recursive call to our DFS function with the new starting vertex of 1. The first thing that happens in this recursive call is we visit vertex 1, which becomes the second vertex in our DFS traversal. Now the key idea is that when we look at the neighbors of vertex 1, vertex 0 is already marked, so we can't make another call to vertex 0. So the only remaining option is to recursively call our function on vertex 3. The process is exactly the same. We visit vertex 3, which ends up being the third vertex in our DFS traversal. Now from here, we can go to vertex 2 or we can go to vertex 4, and the choice we make here is arbitrary. Let's say the algorithm picks vertex 4 first. This means that we have another recursive call with the starting vertex now assigned to vertex 4.
Hey,
We then
appreciate
visit
you, Kami.
vertex 4, which
Appreciate
is the fourth vertex in our
It's
traversal.
easier to do a bunch of leak code
Now at this
problems
point in
that
the
have to
recursion,
do
we
with
now look at
graph
all of vertex
traversal
4's
first,
neighbors,
then
which
do
includes
things like
only
the
the
chess
vertex
problem.
3. But
Since
notice that
solving
vertex
the
3 is
chess-
already marked, so what that means is at this point there's
Since
nothing
doing
further to
the
do in this
chess
call,
problem
so we go
involves
back to the
creating a
previous
graph
call of the
and then
DFS
traversing
function
it
on the
to
starting
solve the
vertex
problem.
3. We had just finished our call to the neighbor
I'll take
vertex
some
4,
leak. I don't
so
have a
let's
leak
now
code account.
evaluate the next unmarked
But damn it,
neighbor.
I'll create
The
one.
only remaining unmarked
Damn it, I'll
neighbor
do
is
it.
vertex 2, so we can make
I'm
a
not
recursive
above it
call to
all.
the function with starting vertex 2.
I'm not
In
above it.
this recursive call, we visit the vertex, and that becomes the fifth vertex in our traversal. There are no more unmarked neighbors for vertex 2, so we can go back to the call on starting vertex 3. Vertex 3 also has no more unmarked neighbors, so we can go back to the call on vertex 1. Same story here, so we go back to our first initial call on vertex 0, which also has no more unmarked neighbors, which means at this point the DFS traversal is complete. Pretty elegant and simple algorithm overall, and I hope drawing out the recursion gives you a better understanding for why this algorithm works. There's one more implementation of DFS that I think is equally important to understand. This is an iterative implementation where we have the same concept of marked nodes as before, but the key difference now is that we will use a stack data structure to keep track of nodes to visit. So at the start, we will initialize the stack with just the starting vertex, and then while the stack is not empty, we'll pop off the last vertex of the stack. If that vertex has not been visited before, we will visit the vertex and mark it accordingly. Afterwards, we'll iterate through the neighbors of this vertex as we did before and insert them into the stack as long as they haven't been visited before. The best way to understand this implementation of DFS is by seeing it in action. When we call this function on this graph with starting vertex 0, we start off with a stack that contains just vertex 0. We then remove this vertex from the stack, and this is consequently the first vertex that we visit and mark in the graph. As a result, it's the first vertex of our DFS order. Now we iterate through all vertex 0's neighbors, and since none of them have ever been visited before, we add them all to the stack. We then go back into a loop and pop off the last inserted vertex, which happens to be vertex 1. This vertex has never been visited before, so we now visit this vertex and mark it. This is the second vertex in our order. Now as before, we go through the neighbors of vertex 1. Vertex 0 has already been visited, so we don't insert it into our stack, but since vertex 3 has never been seen before, we'll put it in our stack. Notice that vertex 3 shows up multiple times in the stack, but that's okay. The marking of vertices ensures that they won't be visited multiple times. The next vertex we pop off is vertex 3, which we then visit, mark, and add to the order as the third vertex. Vertex 3 has 4 neighbors, but only neighbors 2 and 4 have not been visited before, so these are the next 2 nodes we add to the stack. After adding these nodes to the stack, the next vertex we pop off is vertex 4, which means it's now the 4th vertex in our DFS order. Vertex 4 has only 1 neighbor in vertex 3, but since that vertex has already been visited, we do not need to add it to the stack. The stack is still non-empty, so the next vertex we take out is vertex 2. This vertex hasn't been visited yet, so we visit, mark, and add the vertex to our order. We've now visited all the vertices of the graph, but there are still 2 vertices in the stack. The algorithm will not add any more vertices to the stack and will eventually pop off the remaining vertices from the stack, but not visit them since they've already been marked. The algorithm will then terminate when the stack is eventually empty. While this algorithm is a little lengthier and more involved than the recursive implementation, using the stack in this manner is a really helpful way for you to organize information if you ever need to identify the DFS order of a graph by hand on a written test or exam. So you've seen 2 implementations of DFS thus far, and I want to make an important note that for all practical applications, both these implementations are equivalent in the sense that they both run in the same running time of O of V plus E time, where V is the number of vertices in your graph and E is the number of edges. As a result, from a performance perspective, if you run either of these algorithms on a huge graph, you'll see no noticeable difference. However, the reason I want to show you both versions is that the recursive implementation is the more standard implementation of DFS you'll encounter since it's cleaner and easier to read. But at the same time, including the iterative approach is important since it's more generalizable to other graph traversal algorithms that require an iterative approach. You end up seeing this logical structure a lot in other graph algorithms, so I think it's a good idea to introduce it here. On the topic of comparisons, let's make a quick note about the differences between a pre-order and post-order DFS traversal. The orders we have looked at thus far are all pre-order DFS traversals. All this means is that we output a vertex as part of the order as soon as we encounter a new vertex. A post-order traversal is slightly different in that we're going to output the vertex as part of the post-order only after there's nowhere else to explore from that vertex. For example, in this graph, the first vertex in our DFS post order is 2 since that was the first vertex where we hit a dead end and had to go back. The next vertex where this happens is vertex 6, which then ends up being the second vertex in our post order traversal. And eventually we reach another dead end at vertex 9, which then becomes the third vertex in our post order. Now vertex 8 is also a dead end, so we can add that to the post order. The previous vertex 7 is now also a dead end, and this continues until we get to the starting vertex. Here's what the rest of the post-order traversal looks like. And as with pre-order traversals, there are several other valid post-order traversals for this graph. The important idea here is to make sure you understand that a DFS post-order will only add a vertex to the order when there are no more neighbors to explore at that vertex. Implementing a post-order DFS traversal is actually quite easy once we have a pre-order implementation. This is what the recursive pre-order implementation of DFS looks like that we just went through. To make it a post-order implementation, all we have to do is, instead of visiting a vertex as soon as we encounter a new vertex, we will now visit a vertex only after all its neighbors have been visited. This idea is reflected by just moving the call to the visit function to the very end of the DFS post-order function. And that's all there is to DFS post-order.
Though, the thing about these algorithms
In the last part of this video,
is everything moves so fast, it doesn't matter what the order is. It's just I just need to know if the order makes said path in question or move possible. And we could check every fucking path. I don't think I'm ever gonna write a line of code that will require me to have an exact pathway set up like this. Now, if it's a race of optimization, then sure. Unless I'm completely wrong on that. It would have been the first time.
I want to talk about some of the applications of DFS. DFS with some additional modifications can solve a ton of interesting problems in graph theory. One example is cycle detection. This problem can be solved by applying DFS with the additional check that anytime you encounter a new edge that points to an already visited vertex, you have a cycle. Another example is finding connected components of a graph, which just requires running DFS multiple times. The main idea behind finding connected components is to start by running DFS on a random vertex. DFS will then find one component. The next step is to then run DFS on an unvisited vertex, which will output another connected component. Continuing this until every vertex is visited will give you all connected components of a graph. Another more involved application of DFS involves finding a topological sort of a graph. This feature applies to specifically directed acyclic graphs. Imagine each vertex in this graph represents a task. If an edge points from vertex 0 to vertex 1 as it does here, what that means is that task vertex, you have a cycle. DFS with some additional modifications can solve a ton of interesting problems in graph theory. One example is cycle detection. This problem can be solved by applying DFS with the additional check that anytime you encounter a new edge that points to an already visited vertex, you have a cycle. Another example is finding connected components of a graph, which just requires running DFS multiple times. The main idea behind finding connected components is to start by running DFS on a random vertex. DFS will then find one component. The next step is to then run DFS on an unvisited vertex, which will output another connected component. Continuing this until every vertex is visited will give you all connected components of a graph. Another more involved application of DFS involves finding a topological sort of a graph. This feature applies to specifically directed acyclic graphs. Imagine each vertex in this graph represents a task. If an edge points from vertex 0 to vertex 1 as it does here, what that means is that task 0 must be done before task 1. A topological sort basically answers the question of how we can find a valid order to execute tasks in a directed acyclic graph. This particular graph has several topological sorts, one of which is to start with task 0, which allows us to execute task 1 and task 4. From here, we can move on to task 3 and then task 5. From task 5, it's important to note that we can't actually execute task 8 until we finish task 7. So we execute task 7, which now unlocks task 8 and task 9. After this, we can go back and complete task 6 and task 2. Again, this is just one possible ordering. There are several other valid topological sorts. This problem can actually easily be solved with depth first search, specifically a DFS post-order traversal with a few modifications. A DFS post-order on this graph will give you the following as one possible output. Do you notice anything interesting? The key idea is that reversing the post-order traversal of a graph will always give you a valid topological sort of the graph, and I encourage you to think about why this trick works. There's a fairly intuitive justification for why this works that I'll leave to you as some food for thought. The last application I want to talk about is kind of just a fun one that I learned about while doing some research and exploration for this video. Turns out that you can easily generate some really cool mazes with DFS. Most mazes have a grid as a foundation, which we can easily represent as a graph. Now, with this graph representation, we can run a modified version of DFS from a particular starting point, such as the top left corner, and check out what happens. What's really cool about this is that the only difference here is that instead of inserting neighbor nodes one at a time in a particular predefined order, we take the set of neighbors of a node and randomly insert them into a stack. When I generated this animation, it was just a couple of lines in difference from the bare bones DFS algorithm. And it really does generate a difficult and beautiful maze. I had a hard time solving it without cheating, so good luck for those of you who want to try.
Get fucked. Starting up top. Dead end. Dead end. That one's fuck, dead end. Dead end. Dead end. Dead end. Dead end. Dead end. This one is completely useless. Next. Dead end. This one's completely useless. That's useless. This useless. This is useless. All of those are useless. Dead end. Dead end. Dead end. Dead end. This is useless. This is useless. This is useless. This is useless. Dead end. Dead end. Dead end. That's useless. That's useless. This is useless. This is useless. Oh wait. Are we supposed to be using the white or the black? He didn't discern.
That's
the black
all for
ones
this
all lead
video,
to
and
dead
thanks
ends.
for watching. If you enjoyed the content, please hit the like button so that this content will be recommended to more people. If you want to see more content like this, please don't forget to hit the subscribe button. And if you want to more directly support the work of this channel, please check out the Patreon page linked in the description below.
Oh wait. I liked it before.
Today I want to go over another key search algorithm in graph theory, breadth first search, or BFS. Suppose you were given a graph with a starting vertex and asked the question of finding the shortest path from that vertex to every other vertex in the graph. The BFS algorithm allows you to answer this question. In this video, we will go over the key intuition behind this algorithm, which will then lead us to an overview of the implementation of BFS. And in the last section of this video, we will go over a practical problem that shows one of the most interesting applications of BFS. Let's get started. One of my favorite ways to think about breadth first search is through the following analogy. Imagine a graph like this one represents balls with strings attached to them. Suppose you want to start a traversal of the graph from vertex 0. What you can do is imagine that you are pulling the ball that represents vertex 0 up until all the strings tighten. The shortest paths between vertex 0 and all other vertices are immediately clear, and the levels of the graph visually show a natural order for breadth first search, where we first visit vertex 0, visit all vertex 0's neighbors one by one, and then visit vertex 5. This was one of those visualizations that really helped the idea behind BFS click for me when I first learned this algorithm. Let's extend this intuition to a more complex graph. Starting at vertex 0, the idea of BFS search is that we are first going to visit a vertex and then visit all vertices of distance 1 from that vertex. After visiting all distance 1 vertices, we then continue with the natural progression and visit all distance 2 vertices. And this continues until we visit all vertices of the graph. Forcing an ordering where we visit all vertices closest in distance from that starting vertex is not only why the name of the algorithm makes sense, but also why it guarantees that the moment we visit a vertex, we have found the shortest path to that vertex. For example, the shortest path from vertex 0 to vertex 7 is discovered as soon as we visit vertex 7. As a result of this property for graphs with equal edge weights like this one, algorithms centered around breadth first search are the go-to method for solving shortest path problems. It's worth noting also that the order in which we visit vertices of the same distance from the start does not matter, so there are many valid BFS orderings. The BFS ordering shown here is one of those valid orders. Let's now take a look at the implementation for BFS. The BFS algorithm is quite similar to the iterative implementation of depth first search we went through in a previous video. We'll first initialize a Boolean list that will help us keep track of vertices we have already visited in our traversal. Initially, all vertices will have their respective marked value set to false. The key idea that is the core of BFS is that we will then use a queue to keep track of vertices that should be visited. While this queue is not empty, we will then remove a vertex from the front of the queue. If it hasn't been visited yet, we will visit the vertex, mark the vertex, and then iterate through all the neighbors and add any unmarked neighbors to the queue. To make sure this is clear, let's go through how the order is generated for this particular graph. Since we start at vertex 0, that's the first vertex into the queue, which is then promptly removed, visited, and marked. This vertex is the first vertex in the BFS order. We then add all of vertex 0's neighbors into the queue, where the order in which they are inserted does not matter. The next vertex we then pop off is vertex 1, since it is at the front of the queue. This vertex is then visited and marked, making it the second vertex in the BFS order. We then iterate through all vertex 1's neighbors, of which only vertex 3 is added since it's the only neighbor that is unmarked. We then go back into a loop and pop off vertex 3 from the front of the queue. This vertex has not been visited yet, so we again visit and mark the vertex. As a result, vertex 3 becomes the third vertex in the BFS order. Going through vertex 3's neighbors, we add 2 more vertices to the queue, vertex 2 and vertex 4. We then remove the next vertex off the queue, which happens to be vertex 2. You know the drill now. Vertex 2 hasn't been visited, so we will visit the vertex and mark it, making it the fourth vertex in our BFS order. We iterate through all neighbors, but we don't add any of them to the queue since all neighbors have been visited. The next vertex that is removed from the queue is vertex 3, but this vertex has already been marked, so we move on. The same thing happens in the next iteration with vertex 2. We now have one remaining vertex in the queue, which is vertex 4. This vertex has not been visited before, so we visit and mark the vertex. This vertex is the final vertex in the BFS order, and after this point, the algorithm terminates since all of its neighbors have already been visited and the queue is now empty. Now that we've seen the implementation, let's take a look at a real-world problem. Suppose we were given an image represented by a grid of pixel values. Let's assume that these pixel values are just integers for simplicity. We are then given a starting pixel location as a row and a column in the grid and a new pixel value p. Our goal is to transform all pixels connected to the starting pixel to a new pixel value. Let's deconstruct what's going on here. Given this set of pixel values, you can imagine a corresponding image where the value 1 represents the color white and 0 represents black. This is quite an oversimplification, but it's one we'll make for now so that we can focus on the important parts of the problem. With this image representation, it's a lot easier to understand the notion of connectivity as it relates to an image. Connected pixels share the same pixel value and have a path between them by moving either left, right, up, or down. So, looking at an example, given a location of row 2 and column 2, our starting pixel is the center of this image. Our new pixel value is 3, and again for simplification, let's assume this is some new color like blue. The goal of this problem is to transform all pixels that are connected to the center pixel to this new color as shown here. Here's another example to further clarify.
If we choose the starting pixel to be row 2 in column 4 with pixel value 5 representing the color yellow, this is what the transform image looks like. For those of you who have ever used a paint application like Microsoft Paint, this is essentially what the bucket tool does to fill a section of your painting or drawing with a new color. Let's now see if we can try solve this problem, which is often referred to as the flood fill problem. Describing this problem as transforming a bunch of connected pixels should be an immediate signal that this could really, underneath the hood, be a graph problem. Also, the fact that, this is a video about a graph algorithm, I suppose that could also be a bit of a giveaway. But in all seriousness,
It was a
remember
giveaway.
that connected pixels have the same value and are adjacent to each other in the left, right, upward, or downward direction. Suppose each pixel in this grid is represented by a vertex, and we take the idea of connected pixels literally and connect an edge between the two corresponding vertices. This is what the resulting graph looks like. And given the following input where we once again change the center.
Okay, he does move at a breakneck speed, but he does give really good information, but we've run out of time. And when I run out of time, it's because I gotta do something. So I ain't gonna hold y'all. Clap it. Take me over to the credits, yo. Hey, yo. Appreciate you so much. I got my buttons back. Shout out to Crumb for giving me the heads up on that. We got the Perfect Stranger and Perfect Lurker. Let's go see what Trycatch is doing. It's been a great week, all around. Great views on the YouTube. Go check out the other YouTube page. Me and Yak did a review. I pushed it out early because I knew I was gonna be busy this weekend. Got a dinner. Got to work on a comic book, the GitHub. All of these things are happening. So a lot going on, but I don't think the credits ain't rolling. We can't have that. End credits. We gonna make that shit roll. Yeah, copy the message because I'm not gonna make it. I'm not gonna make it. Roll credits live. Tag, copy the message, please. Shit. Can't find the screen. Oh god. Okay, I think I can copy one. It's not the right one, but yeah, I got the other one. Okay, cool. So everything's in there now. If you do see me this weekend, we'll be playing some video games or working on a comic book. Really appreciate all y'all support this week. 3,000 views, 400 hours. What more can a man ask for?